Hello and welcome. This video serves to help with AP Physics 2 homework, electric potential and electric potential energy. Get your calculator and let's begin. Remember, use my tutorial as a way to serve as a template for how to solve your problems. If you get a question wrong, go back and try it again with a new set of data until you get it right. Our first question is called charge causing voltage. Put your name in the program and let's begin. So for me, my sensor A, so the first thing you're going to do is you're going to label your sensor A and B. My sensor A is at 1.6 over and 0.8 down. There's my A. And my sensor B is located at 1.7 to the left of the origin. There's my B. Okay. And my charge is located here. I just don't know what the charge is. So the first thing I'm going to need to do is I'm going to need to find that distance right there. A little Pythagorean theorem is required. Okay, so for me, I'm going to be going 1.6 squared plus 0.8 squared, square root that, and I have a distance of about 1.79 meters. Okay, now I'm going to use that to find my charge. So voltage is equal to K times Q over R. But remember, I'm solving for Q first, so I have to get rid of K and R. You can see I can do that by multiplying both sides by R and dividing both sides by K. So voltage equals V times R divided by, oh, no, sorry, not voltage, charge. We're solving for charge. Equals voltage times R divided by K. Well, the voltage in my case was 2017. So the voltage at A is where you're starting. We're going to take the voltage at A times the distance. For me, it was 1.79 divided by 9 times 10 to the 9. All right, and I'm getting a charge of about 4.01 times 10 to the negative 7. Now we're supposed to answer in nanocoulombs. So to do that, we just have to move the decimal twice to the right, and it's 401 times 10 to the negative 9 coulombs, which is the same thing as, in my case, 401 nanocoulombs. So that's my charge. I know it's positive because I have a positive potential. Now, if I take that and put it back into the same equation, I can figure out the potential at B. 9 times 10 to the 9 times my charge, 401 times 10 to the negative 9, all divided by the distance to B, which is 1.7. And for me, I'm getting a value of about 2,123 volts. Let's go ahead and check. My charge was 401. My voltage was 2,123. And there you go. Hopefully you were able to get question 1 correct yourself. If you didn't, go back and try again. If you did, let's move on to question number 2. Now, question number 2 is called voltage from 2 charges. So you're going to give 2 charges at different distances. Mine are 509 and negative 472. My 509 charge, Q1, is at 1.1. So take a second to put where your charges are. Mine's at 1.1. That's positive. And my second charge is at, looks like 1.8 to the right. and that's negative. 509 and 472. Okay, we got that. Now my sensor location is at 1.4 down on the y-axis down here. So put your sensor location on your graph. I'm going to call that point P. We got to find those distances. Call this R1. We'll call this R2. The only thing we have to do is a little Pythagorean theorem to figure that out. So for me, R1 is going to be 1.1 squared plus 1.4 squared. And then when I square root that, I get 1.78. And then for R2, I'm going 1.4 squared plus 1.8 squared. And I'm getting about 2.28 meters for that one. Okay, so that's the first thing I have to do is enter in my meters. So 1.78, 2.28. 1.78, 2.28. Now I got to find the voltage. Well, to find the voltage, that's actually pretty easy because I just got to find the voltage to each one. Okay, voltage 1 and voltage 2. That's going to be KQ1 over R1, and voltage 2 is going to be KQ2 over R2. So I'm going to go 9 times 10 to the 9 times my Q1 charge was 509 times 10 to the negative 9 all over its distance, which was 1.78. Okay, and my bottom charge, 9 times 10 to the 9 times, looks like we're going 472, negative 472 times 10 to the negative 9. Remember, positive charge, positive potential, negative charge, negative potential. So you will put negative charges into this equation. And then 2.28 was the distance. Okay, go ahead and take some time to calculate your potentials. Okay, so those are my voltages. My net voltage is just the arithmetic sum, adding them up. So it's 2574 plus a negative 1863. And I'm getting a net of about 711, positive 711. Okay, let's put that in there. All right, and there you go. Hopefully you were able to get question 2 correct as well. If not, try it again. If you did get it right, let's move on to question 3. Now, question 3 is called electron fired by a capacitor. Go ahead and put your name in the program and let's begin. So in this one here, we're going to get an electron that's going to start from rest from the negative plate. So there's a negative plate over here. It's going to accelerate over here to the positive plate on the other side, and then it's gonna fly across to that screen, in my case, 66.8 millimeters away, at a constant speed. So it's going to accelerate in the first region and move at a constant speed in the second region. So our first job is to find the speed when it emerges from the hole, and then the second thing we do is have to find the time it takes to travel the whole way. All right, so there's some work to do with this. Let's break it down. Well, first thing I'm going to do is label our values. My voltage is 140. That means 140 on the positive side and 0 on the negative side. So that means the potential difference is 140. Okay, now I have an electron, so I need some values. The charge of an electron is 1.6 times 10 to the negative 19, and the mass of an electron is 9.11 times 10 to the negative 31 kilograms. These are things that are found on the table of information. Sorry, let me go ahead and fix this. All right, so now see the rest of my values here. Oh, I need to record some distances. So for me, 13.2 millimeters. So 13.2 millimeters and 66.8 millimeters. Okay. Okay, what else do I need to record in here? That would be it. Okay, so how do we find the speed? Well, for that, what basically happens is the potential energy, the electric potential energy, which is Q times V, that the electron has, it has the potential to move here, but it's not moving yet. That will transform into kinetic energy as it as it reaches the hole here. So in other words, we're going to use conservation of energy to find the speed. So conservation of energy tells us that energy initial equals energy final. The initial energy is electric potential energy. The final energy would be kinetic energy as it merges through the hole. So the electric potential energy is Q times V. The kinetic energy equation is 1/2 m little v squared. And you guys are looking for the speed right there, little v. How do we solve for that? Well, you're going to multiply by 2 to get rid of the half, divide by m, and square root. So little v is equal to the square root of 2q times the voltage divided by the mass. So let's figure out the speed. So 2, the charge of an electron, 1.6 times 10 to the negative 19, times your voltage. In my case, it's 140. Divided by the mass, very small mass, 9.11 times 10 to the negative 31. Go and put that in your calculator. Figure out your speed. All right, so I'm getting 7.01 times 10 to the 6 meters per second. So that's the speed I'm getting. Okay, so let me enter that in. 7. So the way I would enter that in, I would go 7.01 E 6. That's how E is times 10. So that's how I put it. Now to find the time in nanoseconds, what you have to do is you have to find the time it takes. I'm going to call this T1. You have to find the time it takes to cross this part. And then you have to find T2, which is the time it takes to cross that part. Well, this is a constant acceleration problem because you're starting from rest and accelerating to some speed. This is a constant velocity problem. Okay, so how do we do that? First, let's find the time it takes to get from the negative plate to the positive plate. That's a constant acceleration problem. And it's also a Newton's second law problem. We got a lot going on here. Okay, now how is it a Newton's second law problem? Well, Newton's second law tells us that net force equals mass times acceleration. Well, the net force is your electric force, which would be Q times E. QE equals MA. But remember, what is the electric field in this situation? The electric field is the potential difference divided by the distance between the plates. So this now becomes Q delta V over D equals MA. So I'm going to go ahead and divide both sides by mass to get A by itself. So A is going to be Q delta V over MD. So I have my charge, 1.6 times 10 to the negative 19 times my potential difference in my case is 140 over the mass of the electron. Everybody's putting in the mass, 9.11 times 10 to the negative 31 times the distance. Now my distance is that little itty bitty distance of 13.2. Now it's millimeters. You got to convert that to meters. So 0.0132 in my case. Figure out your acceleration. I'll figure out mine. And you should get a very high value for acceleration. Okay. So my acceleration is about 1.86 times 10 to the 15 meters per second squared. Now we need to use this to solve a constant acceleration problem. Now, when you have a constant acceleration problem, you're going to make a list of 5 variables. So for constant acceleration, we make the following list. Delta x, that's the displacement. V final, that's the velocity. V initial, that's the initial velocity, which will be 0 because the charge starts from rest. A, which you just found, 1.86 times 10 to the 15, in my case. And T, which is what you're looking for. Now, delta x, I claim you know that. That's the distance across, which in my case is 0.0132 meters. It's this distance right here across the gap. Now, the equation we'll need is we're looking at distance as a function of time. So we can use the equation delta x equals v naught times t plus 1/2 times a times t squared. V naught t cancels because V naught is 0, 0 times time is 0. So delta x is equal to 1/2 at squared. Now to solve for time, you're going to have to multiply by 2, divide by a, and then square root. So time 1 is going to be 2 times delta x divided by a. So 2 times 0.0132 over 1.86 times 10 to the 15th power. Then you have to remember to square root that. So 2 times 0.0132 divided by 1.86 times 10 to the 15. And if I square root that, do that again, 2 times 0.0132 divided by 1.86 times 10 to the 15. And then square root. So I'm looking at 3.77 times 10 to the negative 9 seconds, which is 3.77 nanoseconds. Okay, so I've got my time 1. Time 2 is much easier because time 2 is a constant velocity problem as the charge moves across here. It's constant velocity because there's no force pushing it. Therefore, it's going to move at the same constant speed. Well, that's easy because now you're just going to go delta x for region 2, the velocity times, and then the time. The velocity is the speed that we got at the end of step 2, which in my case was 7.01 times 10 to the 6th power. We're looking for T2. And in my case, delta x was this distance of 66.8 millimeters. So 0.0, whoopsie, just easier if I look here, 0.0668. 0.0668. Okay, now velocity equals displacement over time. So to solve for time, we switch that out. Displacement over velocity. And we're going to go 0.0668 meters over the velocity, which was 7.01 times 10 to the sixth meters per second. Okay, time 2, 0.0668 divided by 7.01 times 10 to the sixth power. And we're looking at about 9.53 times 10 to the negative 9 seconds, which would be 9.53 nanoseconds. So the total time, T total, just add them up. In my case, it's 3.77 nanoseconds plus 9.53 nanoseconds, not nanocoulomb, sorry, nanoseconds. So 9.53 plus 3.77 gives me 13.3 nanoseconds. Let's see how I did. It's going to run the simulation, accelerate. You can see it's moving at a constant speed across. And when it gets to the end, it's going to tell us whether we got it right or whether we got it wrong. And there you go. Hopefully you were able to get question 3 correct yourself. Okay, on to question 4. Question 4 is called work due to a moving charge. Put your name into the program and let's begin. Now for this one, you're going to first have to find the distance, okay, between A and B. So what you're doing is a stationary charge is placed at the origin and a second charge is going to move from point A. You can see where my point A is way over 1.5 over and 2 meters down, all the way over to position B. So you're going to move a charge relative to a stationary charge. The question saying is how much energy will be added to the system. Okay, so first let's find the distance. The distance between A and B can easily be found by just using Pythagorean theorem. So first, on your graph, make sure you note where these points are. So sensor A for me is 1.5 over and 2 down. There's A. And for me, sensor B is 1.3 over and 0.4 down. Let me just double check that. 1.3, yes, okay. Now, to find the distance, it's quite simple. We're just going to go over, just count over. So 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to go all the way over and all the way down. So that would be 15. Let's see. So this would be 0.5, 1, 1.5, 2, 2.5, 2.6. So that would be 2.8 and 2. Okay, so use a little Pythagorean theorem to find your distance. So I'm going to go 2.8 squared plus 2 squared. And my distance should be 3.44 meters. Okay, so that's kind of what I'm looking at here. There's B, there's my A. Okay, so my distance would be the square root of 2 squared plus 2.8 squared, in which case I'm getting 3.44. Okay. Now, 3.44 is in centimeters. You gotta be careful. It's in centimeters. So you got to convert that to millimeters. So to move from centimeters to millimeters, you're going down the stairs once, which moves the decimal once to the right. So for me, 344 or 3.44 centimeters, that's going to be 34.4 millimeters. Now, to find the work done, what we're going to do is we're going to find the potential energy at position A and then again at position B. So potential energy at position A is K Q1 Q2 over R. And then the potential energy at position B is K Q1 Q2 over R. RA, RB. The work is just going to be the change in our potential energy. We'll just subtract them. So we got to find these energies. So we're going to go 9 times 10 to the 9 times. Now, charge 1 and charge 2, label that information. Label that information here. So for me, the stationary charge, whoopsie, the stationary charge is 623. Okay, so we're going to go charge 1 times charge 2. So that's, in my case, 623 times 453. 623 times 10 to the negative 9 times, what was it, 453 times 10 to the negative 9, all divided by the distance from the origin, the stationary charge at the origin, to point A. Okay, so that distance was, let's see, did I find that distance yet? I did not. Let me find those distances. Okay, so the distance, let me erase this real quick. Find the distance to point A and the distance to point B. So, sorry. There we are. So the distance to point A looks like it's going to be over point 15 and down point 20. So use a little Pythagorean theorem there. 15, sorry, it's not 15, it's 1.5. So 1.5 squared plus 2 squared, and then square root that. So that distance to A, RA, would be 2.5 meters. Okay, RB, we got to find that using Pythagorean theorem this way. So for that one, I'm going to go 1.3 squared plus 0.4 squared, and then square root that. So I'm looking at RB is about 1.36. Okay, so now my RA was 2.5. Okay, and then I'm going to do the same calculation here. Both of them, in my case, both of them were positive charges. So my energies are positive, but got to plug in my values. 9 times 10 to the 9 times, again, 623 times 10 to the negative 9 times 453 times 10 to the negative 9, all divided by, in the case of RB, the distance to B was 1.36. Okay, so let's find those values. All right, so for the first one, okay, we have a distance. Now, oh, the distance, oops, I almost made a mistake there. The distance is in centimeters. I got to convert that to meters. Glad I noticed that first. Could have been a mistake. So the distance is really 0.025 and 0.0136. All right, that makes a difference. Let me fix that. There we go. So my energy, the potential energy of the charge at position A relative to the origin is 0.1016 joules. Okay. At point B, it's going to be 0.1868 joules. Okay, so to find the work done, just take the difference in the energy. So 0.1868 minus 0.1016, 0.1868 minus 1016 would be just do that one more time, 0.1868 minus 0.1016, 0.0852 joules. Okay, now it wants the answer in millijoules. So to convert from joules to millijoules, just simply move the decimal 3 places to the right. So it'd be, in my case, 85.2 millijoules. Right, there we go. Hopefully you were able to get that correct as well. All right, if you got this correct, let's move on to question number 5. Okay, speed. Let's see, speed charge from repulsion. Okay, speed of charge from repulsion. Let's go ahead and put our name into that and we'll begin. So we're going to be given 2 charges. You can see both of mine are positive, so they will repel each other. The mass of the second charge is 2.5 grams. So first, write down the values of the charge and the mass. It's at 21 millimeters. There's charge 1. There's charge 2. Charge 1 is 387. Okay, charge 2 is 538. Okay, and wrong one. And the mass is 2.5 grams. Now we need to convert that to kilograms, so move the decimal 3 places to the left, and that's 0.0025 kilograms. All right, so here's what we're going to do. First, we're going to calculate the stored energy at the 2 charges at point A. So point A is right here. Okay. Now point B, you can see for me, point B moves all the way to 53. So point B is all the way over here. And at this point, you can see the charge is moving. Now at position A, the speed is 0 because the charge is being released from rest. Therefore, the kinetic energy is 0. So that means the total potential energy is K Q1 Q2 over R. And if I add those together, that's my total energy. So my total energy at point A is literally just going to be the potential energy that it starts with. So that's what I'm going to find first. Total energy at A is only the potential energy at A because the kinetic energy is 0 at A. And that's K Q1 Q2 over R. So we're going to go 9 times 10 to the 9 times charge 1, 387 times 10 to the negative 9, times charge 2, 538 times 10 to the negative 9, close parentheses, over the distance is 21 millimeters. So it's 0.021 meters. Don't square it. And so the energy and the potential energy at A, which is the total energy, let's go ahead and find that. All right, I'm getting a value of about 0.0892 joules. Okay, that's the energy at point A. Now at point B, my charge moved to 53 and it's moving, which means the total energy at B is now going to be the potential energy at B plus the kinetic energy. It's going to have kinetic energy because it's moving. Now, the total energy has to remain the same. So the total energy at B is the same as the total energy at A, which we just found. So the total energy at B equals the total energy at A, which is the value we found 0.0892. 0.0892 joules. But the total energy at B is equal to the kinetic plus the potential. Okay, now we can calculate the potential pretty easy because we have two charges and we have the distance between them. So we can figure that out. And once we figure that out, we can then figure out the kinetic energy. Once we figure out the kinetic energy, we can then use that to find the speed at point B. So in step 4, we're going to calculate the stored energy at point B. So let's do that. Stored energy at point B is going to be K Q1 Q2 over RB, which we're going 9 times 10 to the 9 times 387 times 10 to the negative 9 times 538 times 10 to the negative 9. Okay, all over, I believe it's 53 millimeters, so that would be 0.053 meters. Okay, so it's going to be less. It's going to be less potential energy because you're farther away now. Let's figure it out. Figure out yours. I'll figure out mine. My potential energy reduced to 0.0354 joules. Well, remember, the total energy at B is equal to the potential energy at B plus the kinetic energy at B. Let's find that. The kinetic energy at B is the total energy at B, which was the total energy at A, the 0.0892 joules, minus the potential energy at B, which you just found, 0.0354 joules. So the kinetic energy at point B, the difference of those two. So we'll go 0.0892. And my kinetic energy is about 0.0538 joules. Kinetic energy is equal to 1/2 mv squared, and you'll use that to solve for V. Multiply by 2, divide by mass, square root, and V would equal the square root of 2 times the kinetic energy over the mass. So 2 times the kinetic energy, 0.0538, divided by the mass. Remember, the mass was really small. It was 2.5 grams, or 0.0025 kilograms. Okay, we're going to go 2 times 0.0538. Divide that by 0.0025. 2 times 0.0538. Divide that by 0.0025. Then I have to square root that, and I'm getting a speed of about 6.56 meters per second. Okay, the energy change is going to be the work that's done. Okay, so the energy change is the difference between the right here, the energy change. So the energy change is going to be your kinetic energy. So 0.0538 in my case. All right, and there we go. Again, hopefully you were able to get question number 5 correct yourself. If you did not, please try it again. If you did, let's move on to our final question. Put your name in, let's begin. This is called close approach, closest approach. Now, we're going to use conservation of energy with this, but going backwards. So think about this. We have 2 positive charges. They will repel each other. So there's only going to be a certain distance that moving charge on the right is going to be allowed to get to the stationary charge on the left before it stops. So this will be our strategy. First, let's actually label our info. So with this, I've got a 475 nanocoulomb charge here. I'll call this Q1. Okay, then I have a 635 nanocoulomb charge at what looks to be 72 millimeters. Okay, 635. And it's moving with a speed of 7.13 meters per second. Pretty slow, considering it's a particle. And the mass of it is 4.8 grams. Right? Which we know to be 0.0048 kilograms. Remember, we have to move that to the left 3 times. So first things first, let's find the initial kinetic energy of that moving charge. That's pretty easy. We're just going to go 1/2 times m times v squared. So 1/2 times the mass, 0.0048, times the speed, 7.13, and then square it. So square the speed times the mass, take half. And I'm getting a kinetic energy for me about 0.122 joules. Go ahead and figure out yours. Okay, now let's calculate the initial stored energy. That's the potential energy. So the potential energy electric is K Q1, Q2 over R, which would be 9 times 10 to the 9 times charge 1 is 475 times 10 to the negative 9 times charge 2, 635 times 10 to the negative 9. All divided by the distance between them is 72 millimeters or 0.072 meters. So my electric potential energy in this is 475 times 10 to the negative 9 times 635 times 10 to the negative 9 separated by 0.072. And I'm looking at an electric potential energy of 0.0377. Now, we got to use these answers to figure out the closest approach. So we're going to use conservation of energy. Now, first we need an initial energy. The initial energy would be the sum of these two energies, potential and kinetic, way far away. Okay, so it's going to be potential plus kinetic. The potential energy was 0.0377 joules plus, for me, it was 0.122 joules. And for me, I get 0.1597 joules per total energy. Well, guess what? When that charge gets as close as it can before it stops, velocity comes to 0, that means the kinetic energy also comes to 0, but the total energy is the same. The total energy final is the same as the total energy over here, which you just found to be 0.1597 for my example. So over here, the total energy is also 0.1597 joules. However, since there's 0 kinetic energy, that and total energy is equal to kinetic plus potential, kinetic energy 0, that means this total energy is really the potential energy at that location. So my total energy final is going to be my potential energy, which is going to be K, Q1, Q2 over R. But to find the closest approach, that means the closest distance. So guys, we'll just solve for R. How do we do that? Swap them out. So R is going to be K, Q1, Q2 over our potential energy. So we're going to go 9E9 times, we're going to go, what's my charge? 475 times 10 negative 9 times 635 times 10 negative 9 all over our potential energy, which we just found to be the same as our total energy initially, which was 0.1597 joules. So I'm going to go 9E9 times 475 E negative 9 times 635 E negative 9, all divided by 0.1597, and I'm getting a distance of 0.016 998 meters. But I need to answer my answer in millimeters. Oh, let's put in my energies, by the way. So my initial energy, my initial kinetic energy was, what was it? 0.122. My initial potential energy was 0.0377. And my distance, right, is 0.06998. But I got to move that 3 spaces this way to go from meters to millimeters. So that's 16.998 millimeters. Okay. It's going to go until it reaches that spot, and we're going to see if we're able to do this right. And there you go. I was able to get this right. Hopefully you were too. I hope you found this tutorial to be helpful to allow you to solve your problems. Thank you. See you next time.